question.
Maybe.
All right, where are we at? Transmission lines. We talk about open and shorted feed lines, coax and open wire, velocity factor, which gets into the electrical length, and dielectrics. Because of the velocity factor and the fact that electrical waves propagate through medium other than free space at lower than the speed of light, the physical length of a coax cable is going to be shorter than its electrical length. So if it looks like it's a quarter wave electrically, which says it's, say, I don't know, 12 inches, then it's going to be maybe 11 inches physically, because of the velocity factor that it's traveling slower. And depending on the coax, it's going to be anywhere from 0.6 something up to like 0.98. Hard line or twin lead would be close to air, so it's up in the 0.95 to 0.98 range, I think. For anybody that cares, the formula to figure it out is there. But essentially, it's the ratio of the velocity in the medium versus the speed of light in free space. And everybody knows the speed of light in free space, right?
Yep.
300 what?
Million meters.
What's the physical length of a coaxial cable transmission line? Why is it shorter than its electrical length?
Delta.
So what is the velocity factor? It's the difference of how fast it travels versus how it travels in the feed line. It's the ratio. If you figure in the dielectric, and the K is the permittivity of it, then it's 1 over the square root of K, which you can look up for different dielectric materials.
I think some of the RG8X, the newer stuff, I measured it at like 77-78% of, which is good.
Yeah.
0.77.
Must be foam.
But the old RG8U is in the 60s.
I think that's 66,
Yeah, 66.
according to the exam.
That's what it measures. That's what it measures.
So what's the velocity factor of a transmission line?
And let's see, physical, electrical, where's that at?
Delta ratio. Which of the following has the biggest effect on the velocity factor?
Electric.
Because it's 1 over the square root of the permittivity constant, whatever that is.
They're just rare.
There it is. So open wire is 0.98. Solid is 0.66, which is probably RG8. I'm not sure what 8X is. It's more flexible.
But it's
So it might be foam.
It's a thinner one.
Well, it's the same size as 8.
Style.
I mean, 50. No, 8.
50.
50. Right. But let's see. It's stranded. I'm not sure I don't remember what the dielectric is. I put connectors on some, but I don't remember. It might be foam. If you're measuring 0.7 something.
I was surprised how bad the RG8U was that I'd been using.
Well, it's not necessarily bad.
Now,
It helps if you're making a phasing line. It doesn't have to be as long.
Now, think about it. How much longer is that gonna add to your conversation? The delay time.
So what's the approximate physical length of a solid polyethylene dielectric coaxial transmission line, electrically 1/4 wavelength long at 14.1 megahertz?
Oh, man.
All right, Jack,
Five,
without the calculator, how do you estimate this one?
5, 3.
Three out.
That's 5. Oh, no,
One divided by.
yeah. Polyethylene was 0.66.
0.66.
3.5.
You're right. And if you have a calculator, you can do it this way.
See, I was just gonna do the electrical link, quarter of a, whatever. Then I saw, ooh, dielectric, oh, this is a conversation. Come on, Tom, yeah.
Michael, are you and Jesse okay with that one?
Yes.
All right.
Yeah.
What's the approximate physical length of a foam polyethylene dielectric? Quarter wave at 7.2 megahertz.
6.9.
Boy, you're Mr. Calculator, aren't you?
Oh, polyethylene.
Yeah.
What's that? 0.8. 0.8, is that it?
Baker.
Ooh,
Oh, somebody disagrees with you.
Yeah, 0.8.
all right, 0.8.
You're easy.
Yeah.
0.8. Uh,
I was thinking 0.7 because you messed me up saying 0.7.
okay.
Yeah,
I guess I can't blame that on Greg. He's the one who brought up 0.7.
yeah.
What's the physical length of air insulated parallel conductor, a half wavelength long at 14.1?
Charlie.
Charlie, 10 meters.
Now, actually, this one, and I worked it twice to make sure, because when you add the velocity factor, it's lower than their answer. Without the velocity factor, it's almost the same, which is kind of weird. But the other ones aren't close, so.
Mhm.
Okay, so foam versus dielectric, foam dielectric versus solid. It has a higher velocity factor. It has less loss. The disadvantage is it has a lower operating voltage. In other words, it will arc over at a lower voltage than a solid dielectric. I don't know how that's necessarily a big problem unless you're talking about putting a lot of power through it, where you've got
Well,
some.
you have that ALS 811 now, so.
Yeah, even that doesn't put out those kind of voltages, I don't think. Yeah. Which of the following is a significant difference between foam dielectric coaxial cable and solid dielectric cable, assuming all other parameters are the same?
Delta.
Yeah, we finally got an all the above. Yep. Not very many in the extra.
Backing up a few presentations back, the folded dipole. I believe its disadvantages that it's monoband. For some reason. When they could have told dipole,
Really?
I think so.
Okay.
I will have to check, but I believe that's.
It sounds reasonable that it would only be resonant at,
So regular dipole, you can resonate at your
right.
evens, yeah, evens.
But basically the folded dipole is a loop
Yeah,
that's a light wavelength long. Okay. All right, feed line loss. Okay. Obviously, you want the loss to be minimum because you're going to lose power. The higher the frequency and the longer the feed line is. Coaxial cable has more loss than parallel feed lines. It's more convenient to use. And unless you're talking about VHF and UHF or very long lines, it's not a real significant factor. I guess if you're doing QRP, where every little watt counts, you might prefer parallel feed lines. Would that be a true statement?
yeah, if you're not portable is a little bit harder sometimes still with the parallel lines.
See, I would think that's very important, though, when you have your radiated power occurring right at the transmitter, with parallel lines, there's a disadvantage. When it travels down the coax and only radiates at a higher point, you're gonna have an advantage. So
But you're only getting part of the radiation off of the feed line.
I know, but it's a significant amount.
I don't know.
Where's the highest current? Isn't that at the base of the right at?
Well, for a dipole, the highest current is at the center. Okay. Which is why you feed them in the center for the lowest impedance. Because impedance is just the ratio of the voltage to the current. So the voltage is zero and the current is maximum.
Going to do some low level reading that's good. CBIC.
Yeah.
RL CBIC.
Yeah.
Read him. What's his call sign? 53 RNL, I believe.
Something like that. Yeah. He did a lot of antenna stuff.
Yeah.
Modeling, and a lot of his models are in with some of in the ARL
Yeah.
extras. If you buy the handbook,
Mm-hmm.
you get to download stuff. He's got a bunch of models in there for all these different antennas. In fact, he wasn't the guy that did the Easy Neck, was he? Can't remember the guy's name. Anyway, all right. So, you want to lower the losses. RG58 is probably the worst thing you'd want to use for VHF and UHF, and especially long lines, because it's got a lot of loss. So how does ladder line compare to small diameter coaxial cable such as RG58 at 50 megahertz? Lower loss. Okay. If we're trying to do matching with pieces of coax, and I need Byron to help me with this one, because it seems to me, if I'm going to say it's an eighth of a wavelength long piece of coax, electrically, I assume, it's going to have some inductive reactance that it's going to present, which is going to be a fixed amount depending on the frequency. So, to my mind, that only lets you offset a particular or a certain amount of inductive reactance at that frequency. And if that's how much you need to offset, that's fine. But if your antenna is much more capacitive than that, it's not going to, I don't understand this one.
Get better.
It could make it better, but I don't know how you can say it matches it unless you were lucky. But anyway, it's a test question. So, And it depends on whether you short it or you leave it open as to whether it appears capacitive or inductive. So you have that option of going either way.
How is this different from the parallel is what I want to know, the parallel stuff.
I don't, other than the fact that it's eighth wavelength.
That's right.
But for a stub, you do the wavelength depending on how, what you want to match. And this is saying like it's fixed. I don't understand this one or the point, but
Well, I guess you're saying, depending upon how much capacitance you need or
inductance, right?
you can do a quarter or an eighth wavelength.
Yeah, I guess it gets you close.
One of them might be closer than the
But
other,
if I use a,
but you want to use something that's harmonically related, not harmonic.
okay, but I could do a hairpin with a sliding short and get there too.
Billion ways to do it.
All right. So, it can possibly match a capacitive or an inductive load. It looks like one of those. In this example, okay, they happen to have a capacitive reactance up here in the load, and they just use a shorted, I assume eighth wavelength stub to get the plus J25. So it would work out in that particular case. So what impedance does a 1/8 wavelength transmission line present to a generator when the line is shorted at the far end?
Yes. No.
Yeah, is it capacitive or inductive?
You said when it's shorted, it's the opposite.
Right.
So that's inductive.
I just think that, for the shorted, you got a continuous piece of wire basically, right? So kind of looks like an inductor. Whereas if it's open at the end, you think of two blades of a capacitor separated from each other, that's all correct.
Okay, that's a good way to think of it.
Why did they use the term generator? Doesn't that mean the same thing as a transmitter?
Yes.
Okay.
I guess it's more technical because it's a source or voltage or power generator. We normally think of them as transmitters, but I guess it could be something other than a transmitter generating a signal. Could be a signal generator. We don't call those transmitters, but it can produce the same kind of waveform. Not a lot of power usually. So what impedance does a 1/8 wavelength transmission line present to a generator when it's open?
Two wires separated. What's that look like?
Charlie.
Unfortunately, you only get one of those if you get it. So you have
One or
to
the other.
remember which is which. Okay, if we use quarter wave transmission line, okay. If it's open, in other words, a high impedance on one end, it's basically zero or low impedance on the other end. And if it's shorted, it's zero on the short end, high impedance on the other end. So just think of the sine wave where when it crosses the axis at zero, okay, if you go 90 degrees or quarter wavelength, then you're going to be at a peak, either positive or negative. Okay, so if it's a half wave, okay, then you're going to do a quarter and a quarter. So if you're shorted and you go a quarter, it's high impedance. If you go another quarter, you're back to looking like it's shorted.
That was not sinking in.
Huh?
So that was not sinking in.
Go look up the old Bell Lab.
So that quarter you're talking 90 degrees.
Right, quarter wavelength.
Very low diffusion.
Right.
Open at the opposite corner.
It's gonna go back to zero. Right. It's either gonna be at a peak or zero.
Yes. If it's a multiple of a quarter wave, it's gonna be a high or low. And even multiples, it's gonna be the same.
It's always gonna be zero.
Well, if you start off shorted, yes. If you start off open and it's a half wavelength long, it's gonna look open. It's easier to visualize on the Smith chart.
Which one?
Segue.
I think it's coming up. I even brought one. The real Smith chart. So what impedance does a quarter wavelength transmission line present to a generator or transmitter when the line is open at the far end?
Charlie?
Want to try again? If it's open, quarter wave down the line, it's going to be low impedance.
Time impedance if it's shorted.
Huh?
Time impedance if it's shorted.
It's shorted, it's hot, it's always just the opposite.
So you get halfway,
Yeah, flash.
then it flips.
So what impedance does a quarter wave present when the line is shorted at the far end? What impedance does a half wavelength present when it's shorted at the far end?
We'll say low. Yeah, bravo.
Baker.
Okay.
Yeah, great point.